This is Mrs. Villette, and this is an intro video for volume. So what we're going to try to do in this video is explore how we could find the volume of an object that has sort of a weird shape. So we're going to be looking at a lime in particular. And let's take a look at the video that I've already recorded, and I'll talk about what's going on here. So what I've done with this lime is I've set up some axes. So I've got the x-axis, the y-axis, and the z-axis coming out of the board. And I want you to take a look relative to the x-axis. This sort of looks like circles. Relative to the y-axis, it sort of looks like an ellipse. And then relative to the z-axis, it also looks like an ellipse. What we want to focus on, our best chance of success for volume, will be to look at this lime with the x-axis pointing out at us because we have these circles here. And we know how to find the area of circles, and it's actually going to turn out that we're doing something related to area. Now, one way that we could find volume is we could take some slices. So let's say n of them. So we could take n slices, we could calculate the volume of each slice. We could add up the volumes. And all of this put together would just be an approximation to the volume. Because there's probably going to be some error or some estimation going on when we calculate the volume of each slice. And what I'm going to show you in this part of the video is I actually took some slices, but I took them relative to an axis that wouldn't necessarily be the best axis. So right now you've got either the y or the z-axis pointing out at you. Okay, and what I did is I've already done the slices, so you can kind of see the slices here. And you can see as I take each slice off that each slice looks kind of like an oval or an ellipse. So let's take a look at one of these. And what I want you to notice is that each of the slices is kind of tapered. So the cross sections are almost little trapezoids. Going back a little bit in the video, you can see that my cross sections are ellipses. Now the problem with ellipses is there is not a nice way, well there is a nice way, but it's not well known, to find the area of an ellipse. And actually, strangely, finding the circumference of an ellipse is actually impossible to do other than doing it numerically. So if we could find the cross-sectional area of this ellipse, so if we could find this amount of area, and then if we multiplied that by the height, that would be an approximation. So that would be the approximation of the volume of that slice. Remembering that our cross-sections, if I flip it the other way, looked something like that. And what we're actually going to do is we're just going to say that's close enough to a cylinder. And so we'll just take whatever that base area is and multiply it by that height. So when we're calculating the volume of each slice, we're going to do a base area, and we're going to multiply that by the height, or we could call that the slice height. That's going to turn out to be like a delta x or a delta y. So now I'm going to show you what happens if we take cross sections perpendicular to the x-axis. So right here I have that toothpick pointing out, and that would be the x-axis. And we can see that when I look at sort of the silhouette here that I am getting these circular shapes. So let's go ahead and take a look at what that looks like. So we're going to take our slices perpendicular to that toothpick, and I'm just going to slice on the other side. Now obviously I'm not going to sit here and have you watch me cut up the whole lime. I'm not going to cut up the whole lime. We're just kind of looking for the concept here. We're not actually going to find this volume. So again, we're seeing that that cross-sectional area is a circle, and then when we flip it on the side, we're still going to see that tapering. So here it is flipped on the side, and you can see that you've got kind of that tapering. and all of the slices have that same basic shape. So if we could find the base area and multiply it by the slice width, we could approximate the volume of each slice, and then we could of course add them up. Now wait a minute, couldn't we get better? What if I had done some thinner slices? So I'm going to attempt now to do some thinner slices with some mixed success. So that was almost too thin, this one almost completely disintegrated, but I think I get a few thinner slices here. So here's one, and when you look, it's still tapered, but it's not as much, still that circle, and that tapering is kind of lessened. So just to refresh, the general concept here is that we are going to take end slices perpendicular to some axis or plane. There are, of course, a bunch of different ways I could have sliced this lime. I could have done something diagonal. I could have done some like cubes and some chunks and added those up. But for ease of actually calculating this with calculus, we're going to try to take slices so that they all have the same basic shape. Then you're going to approximate the volume of each slice, and we're going to say the volume of the ith slice is the cross-sectional area. So we're going to suppose that this area depends on where you are, so the x is where you are in the ith slice. So you could have done, when we looked at those sort of tapered cylinders, you could have done the bottom area, the top area, you could have calculated the area in the middle. Whatever you're doing is your representative area. So when we did rectangles before, we were using representative heights. Here we're doing a representative area. And then we're multiplying by the delta x, which is the slice thickness or width. Then you are going to add up all those volumes, and those first three steps, those would be an approximation of the volume. If you want to get an exact volume, you need to let your number of slices go to infinity. And what's going to happen there is you are going to have started with a sum from I equals 1 to n, a of x sub I delta x, and then you are going to let the limit as n go to infinity, turn that into an integral from a to b, a of x dx, where this a of x is your cross-sectional areas. So what we're going to need to figure out is how to calculate the area of a representative slice based on where we are. So let's say we are looking at our kind of lime situation here, and we have x, y, and then we've got the z-axis coming out, and we've got like our lime doing something like this. It's not perfect. This is actually called an ellipsoid shape. But what we want to be able to do is say, okay, if I'm here on the x-axis, what does a cross-section look like here? Well, a cross-section looks like a circle, so this would be our representative cross-section. And if I wanted to find the area of that cross-section, in this case, what I would need to know in order to find the area is I would need to know the radius of this representative circle that I'm using. So this would be an radius that depends on where I am. So right here on the x-axis is my x sub I, and then right here is my radius of that circle. So for here, I could do my area at x sub I would be pi times whatever this r at xi squared is, and so that's what I would be setting up to do my integral. We'll do some more examples of actually calculating this next week. For now, I just want you to get an introduction to the basic idea, and one of your assignments is also going to be to go find an object in your house where you could take cross-sections relative to an axis and get either circles or washers. And so what I mean by washers, kind of like when you guys did the ribbon thing at the beginning of the year, those washers look like that. So a circle with a missing circle in the middle.